Okay, second installment, young people. Here we go about the modern atomic theory, or the quantum mechanical theory, or wave theory of atoms. So we've talked a little bit about the fact that, Planck and Einstein and Bohr came up with these ideas that kind of merged this idea that electrons, which are particles, and light, which is a wave, somehow is related, and Bohr couldn't quite get it all to come together. So it took a little bit more. It took de Broglie, it took Heisenberg, it took Schrodinger, and some other people to come up with a way to merge those two ideas together, that electrons that are particles behave more like photons or light, which are waves, and that electrons could have a dual nature. And so using that idea of dual nature, they came up with something that is really interesting. So the quantum or wave mechanic theory was born from an equation that was developed by Erwin Schrodinger. Schrodinger applied the idea of electrons behaving as waves instead of just particles to atoms. And when he did that, he developed the wave equation. And this is the wave equation. Quite complicated, okay? Quite complicated the wave equation is. And all of these things mean something a little different. And, these whole symbols up here, these are differential symbols, which means I have to do some calculus to be able to figure this out. So in the end, basically, this gives a solution with a set of mathematical expressions called wave functions. And you can see the psi here. This is the Greek letter psi. You can see it here. You can see it here. And you can see it here. So you can see three separate wave functions or sets of expressions that we're going to get to define electrons and where they are and how they behave. Okay, each describes an allowed state of an electron. In other words, where is the electron allowed to be? That's what it's talking about. So where an electron is allowed to be. These are probabilities. These aren't exactnesses. It just gives us an idea of where they might be about 90% of the time. So 90% of the time we should be able to find the electron somewhere within these spaces that the set of functions that we're being given define. Well, the problem is that not everything was kosher, and we'll look at that equation in just a second. Because we couldn't know everything about the electron, and Heisenberg came up with this idea of defining the natures of electrons is really difficult because we can't know exactly where it is and how fast it's moving at the same time. And this is where Schrodinger's cat comes in, this whole idea that if I have a cat in a dark room and I'm throwing balls at this cat in this dark room, I can figure out where the cat is. When I hit the cat with the ball, I'm going to hear meow. The problem is I don't know where the cat has gone or how fast it's gone because I can't see it to know that, but I know where it was. And so we can't know everything about the electron. So we get this equation that you see here, the change in position times the change in momentum, and you'll recognize this mv, this is the equation for momentum, is somehow related to Planck's constant over 4 pi. It's greater than or equal to that. And so we know that we can't know everything. So we define electron energy exactly, but we accept the limitations. We don't know the exact position. We know kind of where it is, but we don't know exactly where it is. We know sort of where it might be, but not exactly, and we have to be okay with that, and that's okay. So quantum numbers. The numbers that are defined by the equation, there were 3 that were defined by the equation and 1 that was added a little bit later. So let's talk about the 3 defined by the equation. It's pretty simple. They represent the shape, the size, and the energy of the orbit. And these are the 3 numbers that the Schrodinger equation first talked about. These are the 3 wave equations as you were. So the first one is n. It's known as the principal quantum number. It's talking about the amount of energy. The lower n is, the lower the energy it has. So if n is equal to 1, it's in a lower energy state. If n is equal to 7, it's in a higher energy state. And fortunately for us, there are only 7. 1, 2, 3, 4, 5, 6, 7 at this moment in time. So L means the orbital or the shape of the orbit. So when we talk about where things are, we're talking about the shape of where things are and where we might find those things and the shape of that. Okay, we're not necessarily talking about, talking about everything. And I'll show you tomorrow in class what I'm talking about in a three-dimensional format of what this shaped thing kind of looks like with one of the p orbitals that I'll show you tomorrow. Okay, and then finally, the last one defined by the original Schrodinger equation was this magnetic, this m sub L. It's a magnetic thing that talks about which particular orbital it's in, and this applies to especially those ones that have multi-lobes. So tomorrow you'll see the P, and it's going to have 3 lobes, and so m sub L defines which one of those 3 lobes that electron can be found in. And so these are the original numbers that Schrodinger came up with. The next number was not defined by the wave function at all. It was added later because we could not identify a single electron. And so it was added later to be able to get down to a single electron within that. And that is the m sub L, or the spin. So we know that electrons spinning in the same direction in an orbital will make things fly apart. There would be too much energy adding together. It'd be like taking 2 large bowling balls and trying to spin them around the same track in a centripetal force. Okay, eventually those balls are going to get lopsided. Something's going to happen and things are going to fly apart. So in order to even things out, we have to have one spinning in one direction and one spinning in another direction. We call it spin up or spin down. They call it spin 1/2 and spin -1/2. Basically, we're having opposites. One going one way, one going the other way. Sorry. There we go. Okay, and that 4th one was defined later. So what does it boil down to? Boils down to this. Electrons and atoms are arranged as levels, N, as sublevels, L, and as orbitals, M sub L. So we have these levels, we have smaller sublevels, and then we have orbitals within those sublevels. And so that's what this boils down to. These are the things that we need to be able to recognize. We don't have to solve the mathematical equation. We just need to know the essence of it. What does N mean? N means the principal energy level. What does L mean? L means the sublevel it's in, S, P, D, or F. We'll get to that in just a second. And M sub L are the orbitals that are within those S, P, D, or F orbitals, okay? So, and then finally the spin is the last one that was added in to be able to say, okay, that's the electron that I'm looking for. So, the last quantum number was defined by Pauli. He basically said no 2 electrons are in the same place at the same time. They have to always be repelling. And this is where we get the spin quantum number. You know, so Pauli was another guy who actually added to this. And he's basically saying electrons cannot be in the same place at the same time. So what does this all mean for us? Okay, it's kind of like defining where we are. If we look at our address, you know, we don't always put country codes because we live in a country that's very, very large. But when you're in another country, there's always a country code, there's always a province code, there's always a city code, and then there's your street. And so when we're looking at the country, we're kind of looking at our energy level, kind of where are we? Where generally speaking are we? And then we get a little closer. What is our sub-level? Which place are we in? That's your state. And then finally a city, and then finally a street. I still can't completely identify you until I get to street number. Now we can get to street number for you, and we can find out where you are. But generally speaking, in a city like Louisville, it might take me a minute or two to find you if I were just given country, state, city, and street. But eventually I would be able to find you unless there were multiple streets with the same name in the same city, which could definitely be. So you get the idea here, country, state, city, street. So if I said United States, Kentucky, Louisville, and then I said Greenwood, you'd have an idea of where to start looking. You might not know exactly where that is. Now, we know that we can give a street number, like 5901. Well, 5901 would put us at PRP High School on Greenwood Road, but we can't get that specific with electrons. So we're going to keep it country, state, city, street. So we're defining that about the electrons, and that's N, L, M sub L, and M sub S. It gives us a lot of information, but it doesn't tell us exactly where it is. It just gives us information about where it probably would be. So if, someone were to ask me, where are you at midnight? Well, I could probably state you're in the United States, you're in the state of Kentucky, you're in the city of Louisville, and you're on whatever street you live on. I can definitely say that. Depending on exactly when it is, if it's like maybe let's say 9:30, you might be headed down the street, or you might be at your best friend's house who lives down the street. But generally speaking, I can pretty much find you there. Okay, so energy levels, N. N is funny because N is defined by the rows on the periodic table for the most part. Okay, so each energy level has a principal quantum number N. Currently, N can be 1 through 7 because there are 7 periods or rows on the periodic table. So if we look at it, the periodic table has N is 1, so all the way across. So these first two up here at the top, that is N is 1. N is 2. N is 2 are this row right here, the entire row, even with the break. So these 10 electrons, or no, sorry, these 8 electrons. N is 3. This is N is 3 right here. And then you would say, okay, and in some cases this is N is 4, but not all of it. It goes a little haywire here. We have a little problem here that we're going to have to work on a little bit later, okay? So basically we're talking rows, especially when we're talking about the tall columns in the periodic table. When we get to the short area in the middle of the periodic table, some things go a little weird. So this would be N is 1, N is 2, N is 3, N is 4, except for right here in the short area, N is 5, N is 6, and N is 7 for all the tall columns in the periodic table. For the short columns, things get really weird. Okay, so orbitals. There are probable spaces. This equation predicts a space, an area, if you will, or a volume, if you will, that the electron will lie in. So far, there are 4 shapes. It predicts more than 4, but remember, we have a finite periodic table. So right now, these are all the shapes we need, S, P, D, and F. So only 2 electrons can be assigned per orbital within that sublevel. So S, P, D, and F per orbital only can have 2 electrons, but they have multiple orbitals, which we're about to find out in just a second. So here's the S orbitals. S orbitals are shaped like spheres, which is probably why they're called S. They're spherically shaped. You can see as I go up in energy, I get larger and larger, which means my electrons are getting further and further away from the nucleus. That's kind of important to remember. So 1s, the electrons are really close to the nucleus. 2s, they're further away from the nucleus. 3s, they're even further away from the nucleus. P orbitals are really funny. They're shaped like dumbbells, okay? P orbitals have 3, or P sublevels have 3 orbitals in them, and they go in the axis directions. If you think about X and Y, we also have a 3 dimensions. Remember, we're in 3-dimensional space, so we have a Z axis as well. So you can see here's our dumbbell, right? And this is 1 orbital. You would have another orbital coming out toward us, straight out, and you would have another orbital going straight up and down. So in the center is where the nucleus is, and that is where no electrons can ever be. So there's a 0 probability of there being an electron right there in the center where the nucleus is. Okay, so here are the p orbitals separately. Here is the X, here is the Y, and here is the Z orbital. Okay, and you can see PX, PY, and PZ. So there are 3 of them. That means, yeah, 2 electrons for each orbital. That's 2 plus 2 plus 2. That's a total of 6 electrons in that orbital. Very good. So 3p orbitals lie 90%. Yeah, doesn't matter. D sublevel has 5 orbitals, and these are really strangely shaped. They are double dumbbells, and they're kind of in the plane. So if we look at them, here is a single D orbital, and notice that they're kind of in the plane of the XY axis, and they're going in between those axes to give you that node. So you're going to have the XY, you're going to have the ZX, you're going to have the ZY, and then you've got 2 that are a little bit creative. So here we go. We have the YZ, we have the XZ, we have the XY, we have the X squared minus Y squared, and we have the DZ squared. So we get what we call a dumbbell with a donut. That's what the chemistry people call that, a dumbbell with a donut. You will not have to memorize these shapes. What you need to know is that the d sublevel has 5 orbitals. And according to what you learned earlier, 5 orbitals means that you have 15 electrons, okay? Or not, I'm sorry, not 15 electrons, 10 electrons, 2 each. Okay, last one, f orbitals. F orbitals get even more complicated. Okay, but there are 1, 2, 3, 4, 5, 6, 7. And yes, this is a dumbbell with a double donut. That's exactly what we call it. Because there are 7, what does that mean? 7 means 2 electrons each. 2 times 7 is 14. That means this guy holds 14 electrons. We're going to stop right there. I think I've given you enough. We're going to come in tomorrow and talk about this a little bit and give you an idea, and then we're going to start talking about electron configurations and what that means to us, okay, and be looking at the periodic table.